Greetings, welcome back to a video lecture series on computer architecture. My name is Dr. Prashant Bachanna. In this lecture, I'm going to discuss about the topics data representation, input-output interrupt, and program interrupt. So we'll see these things one by one. So data representation. So in the computer system, that is in the architecture, so the computer understands only the zeros and ones. So there are different types of data representation. That is, we can represent the numbers in the different types. That is, there are different types of this. So we'll see these types one by one. So the first number system is the decimal number system. So in the decimal number system, so any number which is written with the radix 10 is called as a decimal number systems. And in the decimal number systems, the numbers will start from 0 and it will end at 9. That is, there will be 10 numbers in the decimal number system, and these numbers are 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Okay, so the strings, let us say we'll take an example of how a decimal number system is represented. So let us say like this number is there, 834.3 is a number. So if you want, so this is a decimal number because all the numbers here are 834. 834.5 is a decimal number. So how it is represented? So after the decimal, whatever number is there, that we have to take that number into 10 to the power of minus 1. Then we have to add this number, and the first number before decimal here is a 4. So before decimal, the number will start from 10 to the power of 0. So whatever number is there, that number we have to write, and this number. So 4 into 10 to the power of 5. Then the next number is 3. So 3 into 10 to the power of 1. Then 8 into 10 to the power of 2. So in the decimal number system, so how it is represented is after the decimal, whatever the number is there, that number we have to take and we have to multiply with 10 to the power of minus 1. And if the number is normal number, 834, then we'll start with this LSB, that is least significant bit, and I will take this number. So the number represented will start from here, that is 4 into 10 to the power of 1, 10 to the power of 1, 10 to the power of 2. So we have to multiply these numbers and we have to get these things. So this is 10 to the power of 0, this is 10 to the power of 1, this is 10 to the power of 2. So this is decimal number system. So in the decimal number system, the number will start from 0 and the 9, and the radix will be 10, and for the conversion we'll be using the base 10 to the power of 0 for the before decimal, and after decimal we'll start from 10 to the power of minus 1. Then the next number system is the binary number system. So as a binary number system, in the binary number systems, the numbers will be 0 and 1. So the computer understands only zeros and ones. So these binary number systems will only be understood by the computer. So all the numbers, whatever the data we are giving, so all that number will be in the forms of zeros and 1, and this will be represented by radix 2. Let us say like 1010. So this number system is represented with the base radix 2. So the numbers here will be 0 and 1. So and how this will be represented is the same way. Let us say we'll take one number here for the binary number system. So here the binary number is 1001. So this is like this is represented like with the radix 2. So this bit is called as the LSB bit, and this bit is called as MSB, that is most significant bit, and this is least significant bit. So how this number is represented is, so whatever number is there, that 1 into 2 to the power of 0, then the next number is 0, 0 into 2 to the power of 1, plus next number is 0 into 2 to the power of 2, plus next number is 1 into 2 to the power of 0. So if we add all these things, we'll get 9. That is 2 to the power of 4 is 8, and then 0 plus this will get the 9. So this is how binary number system is represented. So in the binary number system, there will be only two numbers, that is 0 and 1. The next number system is the octal number system. So in the octal number system, as the number represents, so octal number is represented with the radix 8, and the numbers here will be from 0 to 7. So in the if the octal number is converted, so here we have to see the number conversion also. So let us say the octal number is converted into the decimal number system in the following way. Let us say this is we'll take an example. This is a number that is 736 736.4, that is radix 8. So 736.8 is a radix 8. If you want to convert it into the decimal, if you want to convert it into the decimal form, decimal number, that is the so what we have to do, so after the decimal, whatever number is there, that we have to take that number. Since it is an octal number, we have to represent after the decimal, whatever numbers are there, we have to start from the 8 is to the power of -1. So here after decimal 8 is there, so 8 into 8 to the power of -1. Then we have to start with the before the decimal point. So what is the first number? 6. So since it is an octal number, we have to multiply with the number into 8 to the power of 1. Next, the number is 3 into 8 to the power of 2. Then number is 7, that is to 8 to the power of 3. So if we add all these three numbers, then the number is 478.5. So here we have converted the octal number into the decimal number. Okay, by taking the ratios of that 8 to the power of -1 and 8 to the power of 1 starting before decimal and after decimal. So this is how the number conversions are done in the data representation. Then the next number is hexadecimal number. So as the name itself indicates, the hexadecimal number is represented with the radix 10, radix 16. That is, here the numbers will be from 0 to 9, and here 10 is represented with A, 11 is represented with B, 12 is represented with C, and 13 is represented with D, and 14 is 10, 11, 12, 13, 14, 15. So the 15. So here the numbers will be from 0 to 15 here. So 10, 11, 12, 13, 14, and 15. So E and F. So the numbers will be represented from 0 to F. So after 9, 10, 11, 12, 13, and 13, 14, and 15 are represented with A, B, C, D, E, and F. So here we will take an example of how a decimal number is converted into the how an hexadecimal number is converted into the decimal number. So here the hexadecimal number is F3. So radix 10. So if you want to convert it into the decimal, what we have to do? There is F3 in the sense F we have to write here F, and 16, since it's a base of 16. 16 is to 1 plus 3 is there here, 3 into 16 is to the power of 0. So the first number here is 3. So we'll start with 16 is to 0 into 3 plus 16 is to 1 into F. So what is F here? F is 15. So 15 plus 16, here 16 to 0 is 1, 3. So the number here is 243, which is decimal. So this is how F3 hexadecimal number is converted into the decimal number. Simply we'll take the number into 16 to the power of 0 and 16 to the power 1, and we'll add these numbers. So this is how an hexadecimal number system is converted into the hexadecimal number is converted into the decimal number. So if you want to convert any decimal number, we'll see the next different types of numbers. So if you want to convert any decimal number, that is decimal number is represented with the radix 10 to any other system. So this is the procedure that we have to follow. That is a conversion from a decimal to its equivalent representation in the radix R is carried out by separating the numbers. So whatever the decimal numbers are there, we have to separate the numbers into the integer part and the fraction part separately, and we have to convert these parts separately. So in the decimal number, if you want to convert any decimal number into the number, so we have to separate the integer part separately and the fractional part, then we have to convert it separately. So the conversion of a decimal number into the representation is done by successive division here. That is the first integer part is converted by successive divisions, and the next fractional part of the radix r representation is accomplished by a successive multiplication of the r and accumulation of the integer obtained. So here the integer part is converted by division, successive division, and the fractional part is converted by the multiplication. So we'll see an example of how a decimal number system is converted into the other number system. So in this example, we have taken a decimal number and we are converting it to the binary conversion. So what is the rule here? So the binary number system is represented, is divided into the integer part and the fraction part. So what is the integer part here? Integer part is 41 and the fractional part is 0.6875. So now we have to convert this integer part and the fractional part separately. Then and we have to represent it together. So first we'll see the integer part. So what is the procedure? So the procedure for converting the integer part is, so whatever the integer part is there, it is converted by successive division. So if we do the successive division here, so by the number, so we will be doing the successive divisions like this, and we'll be doing till we get the remainder 0. So once we get the remainder, we have to stop and we'll take the numbers from here. So 1 0 0 1 0 1. So by successive division, so we have got this number. The fractional part. So the fractional part, for the fractional part, we have to multiply by 2 here. So here we'll be dividing it by the 10 and by 2 here. So 2 if you divide 2 by 41, so 20 will get. So each time we have to divide it. So for fractional part, what you have to do is, so we have to multiply the number each time by 2 till we get the value 1. So if we get like all the fractional part, all the bits are 0. So if all the bits are 0, then we have to stop the multiplication. So then whatever that number is there, that number will be converting. So this is how we'll convert, and these numbers will be taken. That is 0 1 0 1 1 is the representation of this part. Then if we'll take one more conversion, if you want to convert binary number into the octal and hexadecimal number. So octal in the sense 8, which is represented as 2 to the power of 3. Right. So here we have taken in the binary number here. So for octal representation, in the octal representation, we represent the numbers from 0 to 8. That is 2 to the power of 3. That is, we'll be dividing, we'll be grouping the three numbers, three in a group. So we'll see this. This is a binary number. So we'll group the groups of 3. So we'll group the groups of 3. Then this 0 1 1 is 3. Then 1 0 0 is 4. 1 0 1 is 5. 1 1 1 is 7. Then 0 1 0 is 2, and this is 1. So the binary equivalent of, so the binary equivalent, the binary number equivalent of the octal is 3 4 5 7 2 1. So this is how we'll convert a binary number into the octal number. Then if you want to convert into the binary number into the hexadecimal, we'll see how it is. So in the hexadecimal number, the numbers will be 16. That is 2 to the power of 4. So we have to group the groups of 4 here. Groups of 4. So this is the binary number. So we have to group the four groups here. This is the first 4th group. Then this is the second 4th. We have to make the groups of 4. This is the third one. This is the 4th one. So if you want to convert an binary number into the hexadecimal, so in the hexadecimal, the numbers will be from 0 to 15. That is 16 numbers. So 2 to the power of 4 is 16. So we have to make the groups of 4. So this 0 0 1 1 is 3. 0110 is 6. 111 is F, that is 15. Then 010 is 10, A. So the binary equivalent of the binary number is converted into the hexadecimal, and the number is AF63. Okay, so by making the groups of 3, and in the octal we will be making the groups of 4, and in the hexadecimal we will be making the groups of 4. So this is how a binary number is converted into the hexadecimal number by making the groups of 4 and representing that number in the hexadecimal number from 0 to F. That is after 10. So 10 is the representative way, and so on with 15 is F. So then in the data representation, the next is the complement of a number. So in there are two types of complement of any number. Let us say R is a number system. So there will be like R minus 1 dash complement and R dash complement. So we'll see these one by one. So that is R minus 1 complement is having the complement is done by R minus 1 and defined as R minus 1 into N. So let us say we'll take an example of 9's complement. So if you want to do a 9's complement of any number, what is the procedure is here is we have to so first you have to take the 1's complement of 1011 and this one. So 9's complement of any number is represented by subtracting the number from the 9. Let us say this is the number 10. So the 9's complement is done by 9 by subtracting the each number from 9. That is the number we get. So whatever number is there, so that number will be getting by subtracting the each number from the 9. And first we'll see the 1's complement of a number. So 1's complement of any number is 1's. Let us say this is 0101. So 1's complement will be is represented by representing 1 by 0 and 0 by 1. 1 is represented by 0 by 1. Then 2's complement is, so if we add 1 to the 1's complement, we'll get the 2's complement. This is how we'll represent the 10's complement. Then if you see 10's complement, what is 10's complement? 9's complement plus 1, 83510 is the number. If you want its 10 complements, means each number is subtracted by 9 and it will be added 1. Then the next topic is the input-output interrupt. So this figure shows the input-output configuration. So here we have seen the input-output. So the input devices, let us see, we have taken an example of the keyboard here. So keyboard is an example of input device, and the printer we have taken. So the next topic is how the input outputs interrupts are done. So this is the keyboard, this is the transmit interface, and this is the input interrupt. That is the input interrupt that is represented by INPR, and OUTR is output interrupt. Okay, so this is the flag input. FGA means flag input. Flag input, and FGO is flag output. So so these input devices, so here is an interface, input configuration. So keyboard is connected with the input interrupt, then the register here, then the output is printer, receiver interface, and OUTR. So that is computer registers and the flip-flops will be there. So the input and outputs are the registers here. So here the FGI will represent the flag input, and FGO is represented as a flag output. And this input and output interface is connected through AC, that is accumulator. So accumulator is a special register which is used for the temporary storage in the computer system. So in the computer register, so what you do, we have the flip flops, and so through the serial communication, there are two arrows are there. This arrow will represent the serial communication path, and the thick arrows will communicate about the parallel. So when so these like input output will work in the parallel communication. That is the input devices and the output devices will communicate parallelly, and these single arrow marks will come. So here the single arrow marks, that is OUTR, receiver interface, and printer are in serial communication. Similarly, the keyboard, transmitter receiver, and INPR will be in the serial communication. So this is how and input output interrupts are generated, and how the communication, how the serial communication and parallel communication is accomplished here. So that is what the terminal sends and receive the serial communication. Then the keyboard is shifted into the INPR. Then the serial information of the printer is stored in the OUTR, output register. So here INPR and OUTR, that is input register and the output register, communicate with the terminal serially and with the accumulator in parallel. So here input register is will communicate in serially, and output OUTR will communicate in serially, and these two input output will communicate with the accumulator in parallel. So here the flag bits are, as I said, FGA means input flag and the output flags. So the flags are needed to synchronize the timing difference between the input output devices with the computer. So this diagram shows the flag inputs are required for when the input output devices are communicating with the CPU. So these flag inputs are required for synchronization of synchronization. So this is how the same thing is represented in terms of some of the instructions here. So here D7 input 3 is there. This is the P1. Then this is the input instruction register where the instruction will be stored. So the instructions will be from the bits 6 to 11 here. So there are some input output instructions are there. So this INP will represent input instruction. So here the flag bit is initially. So let us say if you write SCR. So here P is this SC. P will represent the clear the SC register. Then in the input register 0, that is flag input is initially set 0. Then the input register will be the content of the input register will be moved to the accumulator. Then in the output that is if you, the output character from accumulator is taken here, that is the flag output is initially set to 0, and the content of accumulator, if you write AC 0 to 7 means 8 bits of data. Here is accumulator is a register which is of the 8 bit size, and the content of accumulator is moved to OUTR, that is output register. Then skip into the flag input. So these are some of the input output instructions which are present in the computer architecture. Then if you want to skip the input flag, so this is an instruction we'll write. So if flag equal to 1, then program counter will be incremented by 1. So PC means program counter. So what is program counter? The function of the program counter is it holds the address of the next instruction to be executed, and each time the program counter will be incremented by 1. Then for skipping the flag output, so this is an instruction that is if so it is represented by SKO. If FGO equal to 1, then PC equal to PC plus 1. Then the next is ION, that is input enable. If you want to make an input enable on, this is the instruction that we present. Then one is represented with IN, means the interrupt is enabled. So the output interrupt is enabled. And if you want to turn off the flag, so that is the instruction is IOF, and the content 0 is moved to the IEN. So these are some of the input output instructions, that is input output, then skip flag, input flag, then skip output flag, then interrupt enable and interrupt enable on and off. So these are some of the topics we have discussed today. So that's all for the today's class. Thank you very much.
Like, share and subscribe. Hit the bell icon for more updates.